So this is a review of an entire differential equation course in the undergraduate level. So this is the part 1 of that. So we can start with the basics. So what we mean by a differential equation? An equation with at least one derivative, at least one derivative, is called a differential equation. For example, so these are two differential equations. So dy over dx. Here x is the independent variable plus x equal y. So y is the dependent variable. So x is the independent variable so that is normally what is in the denominator. And then y is the dependent variable. So when you have an ordinary differential equation, there's only one independent variable. If there are more than one independent variable, we call it a partial differential equation. We can talk about that later, but that's not the topic of this course. Good. So another example. So for example, this one, 3 d squared y over dx squared plus 5 dy over dx minus y equal 3. So this is another differential equation because there's a second derivative and the first derivative, and then this is an equation, so it's a differential equation. Okay, and then the next thing is what we mean by an initial value problem. So the next one is initial value problem. So in short, we call this is IVP. So when you see IVP, that means initial value problem. So what's the initial problem? Initial problem means a differential equation and a initial condition. So initial problem means a differential equation plus initial condition. So if you are given these two information and ask you to solve the problem, we call it the initial value problem. So initial value, it can be more than one value depending on the order of the differential equation. If it is first order, one initial condition. So let's write that. So if it is first order, we need one initial condition. And if it is second order, we need two initial conditions. So initial means it given at the starting point. So for example, let's say there's a system that can start at t equals 0. So if the information given at t equals 0, we call it the initial condition. So normally like it looks like y0 or x0 if x is the dependent variable. And then there's another type of problem, what we call boundary value problem. So what happened, it can give you values not just at the beginning but some other point. So just write it just for completeness. So what we call boundary value problem. Boundary value problem. In this course actually we did both. So it's called BVP, boundary value problem. So it's a BVP. That means so you can see the conditions not just at 0, but at some other point, like maybe like t equal b or something. So you can say, for example, y b equal something, like why not? So that is what we call a boundary value, boundary condition. Boundary condition. So initial condition looks like y0 equal something, like a y1. Yeah, that's not really the right notation, but yeah, something like that. So if that is the case, so if you get a boundary value, then we call it a boundary value problem. If you get initial value, we call it an initial value problem, like that. And then depending on the degree of the degree of the differential equation, you need to give that many conditions all together. So if it is first order, you need only one condition. If it's second order, you need, I should say, at least two conditions, but two is like, yeah, two is the minimum. So if the nth order differential equation, you need n many conditions. Okay, so that's throughout the course. We're gonna use that fact. Good. Now let's focus on the topics. So we're gonna go one by one, and these can reflect the lectures. So in the description, you're gonna see link to the entire lecture. So part by part. So that means if you have some trouble understanding certain topics, you can refer the lecture. Okay, so let's start with the first topic. So we're gonna go with what we call the first one. What we did was like a verifying solutions. So let's start with that. So the first topic is we're gonna do verifying solutions. Verifying solutions. So what happened here? We are not going to find the solution. You are given some expression, and you're gonna check whether that is a solution. So that's the idea. And we're going to solve the problem later. So let's look at a problem like this. An example like that. So let's say verify that. So remember, we are not say find, we say verify. So the solution is given. Okay, so it's a different problem. We are not going to find it. We just verify. So we need to understand the wording here. Verify that x equal c1 e to the minus 3t plus c2 e to the 2t is a solution of x double prime plus x prime minus 6x equals 0. So first verify that that's a solution. So what we normally do is we take the derivatives and plug into the left side and simplify and show that you get 0. That means it satisfies the differential equation. That means that is a solution. So what you did was we verify. We did not find it. Actually, we know how to find this one later when you talk about second order constant coefficient differential equation, but that's not the point here. We just verify that that's a solution. Okay? Because sometimes you can guess. So that's the point. Especially when there are very difficult problems. Okay, so find, and then we can say find C1 and C2 such that normally we put s dot t dot, but right now this is the first time here, so I will write such that, but later it's be s dot t dot. Okay, such that x0 equals 0 and x prime 0 equal negative 10. It can be just some numbers. So it doesn't really matter how we do it. But let's see how we can do this. Okay, so the answer, let xt is I'm going to exaggerate, that is a function of t. C1 e to the negative 3t plus C2 e to the 2t. So we're going to use that. And then what we can do, taking derivatives. So taking derivatives, we have x prime t equal. So when you take the derivatives, the e function, what happened? So let's recall the results from Calc 1. If you take a derivative of an exponential function with the constant here, what's going to happen? The constant come out and nothing happens to the rest of the function. So that's the result. So k e k t. So k has to be a constant. Okay, if not, then you have to use the chain rule. Okay, so we can use that fact here. So that means the negative 3 C1 e to the negative 3t plus the same thing 2 going to come out. So e to the 2t. We need the second derivative as well. So let's find the second derivative as well. So the second derivative is we multiply by another negative 3, that means become 9 C1 e to the negative 3t, no change, plus this becomes 4 C2 e to the 4t. Oh, see, we can make mistakes very easily, so be careful. It's 2t, no change. Good. So now what we're gonna do is we're gonna substitute. So we simply substitute that this in the differential equation by substituting into the equation. So what we can do, we can start with one side, okay? Into the equation x double prime plus x prime minus 6x equals 0. What we can do, we can start with the left side and see what's going to happen. So let's start with the left side. So x double prime plus x prime minus 6x equal. So let's start with x double prime, which is 9c1 e to the minus 3t plus 4c2 e 3t. That's x double prime, and x prime, which is negative 3c1 e to the negative 3t plus 2c2 e 2t. That's the x prime, and then minus 6x. So that means you have to multiply x with a minus sign. So that means a minus. So let's multiply by minus 6. So it's minus 6c1 e to the negative 3t and then minus 6 c2 e to the 2t. Now what we can do, we're going to see whether you're going to get 0. So let's see. So let's go with e to the negative 3t terms. If you look at e to the negative 3t terms, we have 9 here. We have 9 and we have negative 3 and we have negative 6, and you can see that when you add them, they cancel out. So those 3 cancel out. Now, so that's gone. And now, actually there's a small mistake. So this has to be 2. Good. Now let's look at the 2t terms. So if you look at the 2t terms, and you can see that we have 4, we have 2, and we have negative 6, and you can see that they all get cancelled out. So that's also cancelled out, but I'm going to cancel it in the other direction so that you know what you did. So don't just cancel in the same direction. One you cancel this positive way, other one cancel negative way, you know, with the slope. So then you know what you did. So that means they all cancel out. So you simply get 0. So it simply cancel out and you get 0. That means your expression is actually a solution of the differential equation. So we can write that. So therefore, so you can say that, therefore, that's how you're going to complete the argument. So therefore, like we doing mathematics means we are making a logical argument. So it's an argument. So like you show the reasons and say the conclusion, the reason and the conclusion. So it's like that. So it's a nice argument. Okay. So let's try to do it like that. It's like much better if you want to do that. Like, okay. So therefore, x equal c1 e to the minus 3t plus c2 e to t is a solution of the differential equation of x double prime plus x prime minus 6x equal 0. So we prove that yes, it's a solution. Now what we can do, now we can use the initial conditions to find c1, c2. So using initial conditions, so we have x0, which is what you do is you plug in to the independent variable, you plug in 0. So that means x0. So wherever you see t, plug in 0. So c1 e to the negative 3 0 plus C2 e to the 2 times 0. So that means we know that e to the 0 is 1. So we know that fact. We know that e to the 0 is 1. So we can use that fact, and then that means you simply get C1 plus C2. But we know that from the condition, it is simply 0. It's given that x0 equal 0. So we use that condition here. Okay. So this is given. This equal 0 is given. Now, what else we need is we're going to use derivative condition. So we know that x prime 0, which is negative 3 c1 e to the negative 3 0 plus 2 times c2 e to the 2 0. Now again the same argument, so you're going to get negative 3 c1 plus 2 c2, but we know that it's given that this is equals to negative 10. Again, this is given. Okay, so it's not our choice, it's given. Okay, now the goal is to solve these two equations. Okay, so so we have these two equations, c1 plus c2 equals 0, negative 3 c1 plus 2c2 equal negative 10. Now I'm going to call these two equations are 1 and 2 because it's going to make it easy. So maybe you learn how to solve these equations when you were in high school or middle school. So there are two methods to solve. One is you're going to solve for one and substitute that in the other one. I do not recommend that method because that's long, pretty long for these kind of things. We are not going to do that. What we're going to do, we're going to try to get matching coefficients because that's much faster. And there's a video just to learn like how to solve these kind of equations, and you can learn more about that if you want to watch that, and even like how to go for 2, 3 like that. So we can use that technique here, the matching coefficients technique. So what's the matching coefficients? What we're going to do, and you can see that especially when you see positive and negative, we try to go for that. It's much quicker. So you can see that in the bottom equations, you're going to see negative 3 here. So what you're going to do in the first one also, you try to get a 3 but with opposite sign. So for example, you try to get 3c1. So if you get 3c1 in the top one, now what we can do, we're going to simply add them. Once you add them, you can see that c1 term going to cancel out. So you simply get c2. So that is the fastest way to solve this one. So that's what we're going to do, what we call matching coefficient technique. Okay, so what we're going to do, by 3 times the first one plus the second one. If you do that, because if you multiply by 3, you get 3c1 plus 3c2. When you add c1 get cancelled, you simply get 3c2 plus 2c2 equal negative 10. And then this says that 5c2 equal negative 10. Now what we can do, we can divide both sides by 5, so you get negative 2. So you can see it's very easily. Okay, you get the answer. And then what we can do, you can pick one of the equations by, but the first one is easy. So by 1, you can see that C1 is simply negative C2. So just plug in the C2 value here. So it is negative 2. That means 2. You don't want to show all these steps, but since this is the first example of this type, I'm showing all these steps, but later we can ignore some of them, some obvious steps. So we're done. Now you're going to complete that. So someone make an order, so you're going to preserve your results in the best possible way. Okay, that's how we're trying to do. That's why we're writing all those words, okay, to make a good argument. So therefore we can say the solution to the initial value problem, to the initial value value problem is we can write that xt which is equals to 2e negative 3t minus 2e 2t. So that is the final answer for that problem. So what you can see that, you know, if you to do this, it doesn't take much time. So it's like maximum it would take like 10 minutes to do all of this. But I'm doing it slowly just to explain everything. But you know, when you want to do that in exam or something, you don't want to, like, we don't explain, like, I mean, we explain, but not like we are not going to take too much time. We just write it fast. Okay, so it won't take too much time. You can see, you can practice and see how long it takes for a problem like that. Okay, good. So that's the first problem. And if you need more, you can look at the first video about that to find more information and what else we did. Okay, good. So let's go to the next topic. So the next topic is what we call the four fundamental equations. So we talk about four fundamental models. So let's talk about that. Four fundamental model equations. Four fundamental model equations. So we talk about four models. And why we did that? Because we know that these models like appear pretty much everywhere in sciences. So it's good to know those four separately. Okay. So the first one, what we did was the exponential growth model. So exponential growth. So that's pretty much everywhere. It's like, bacteria, even like these days COVID, all of them follow the exponential growth model. And then, so the differential equation is dy over dt. We can use the t as the independent variable. It's a time. It's it's like kind of makes sense. So k is a constant. We assume k is positive. So, and then we know that the solution of this one is we can write as yt equal a constant times e to the kt. So that's the solution, and you can remember, you can use this. And you know that even we can solve this very easily. This is like a separable differential equations, or we can even use a simple calc 1 technique to solve this one. Okay, it's not a difficult problem. Okay, so now if you look at the solutions for the graph of this one, so what is the graph of this? This is exponential growth. That means you can start at a value and then it's going to grow. So this is what we call the exponential growth model. That's the starting value a, okay, and then it's going to grow. So we assume that k is positive, is a growth. Okay, that's the first case. And then we talk about the what we call exponential decay. So exponential decay. Exponential decay model. So as exponential decay is very similar, dy over dt, and then we assume that k is positive but with a negative sign in front like that. So it's pretty much similar. What's going to happen? There's a negative sign in front. So the e negative kt. So that's what happened. And so if you look at the graph, very similar. But what's going to happen now is it's going to decay. So you can start with a value and go down. So so like that. You can see start with a value a and then go down. So you can see this is exponential decay, and we assume that k is positive again because we put a negative sign in the equation. So that's what we call exponential decay. Especially like if you look at radioactive material, it's going to follow this kind of pattern. There are a lot of other things like even bacteria. If you kind of put like a disinfection there, and those bacteria are going to kill, and then if you look now, if you try to count, so it's going to follow something like that. So these models are everywhere. Like if you get an injection, what's going to happen? So those are the kind of models for that. So it's very common situation. It's called exponential decay. And then we talk about the next most common one is what we call the simple harmonic motion. So simple harmonic motion. Sometimes we call SHM. Okay, simple harmonic motion. So what is the differential equation? There's a slight difference now. This can be a second order differential equation. We have like d squared, and then we're going to use a time variable. Let's say time equal. So we can write negative. There's a negative sign, and a k squared y. So remember earlier you had a t. Now this is y. So that's the major difference here. That's the dependent variable comes here. And then we know the solution. So the solution is with sine cosine. So some number, and then we have cosine kt. So k is the square root of that term. So you see, you have to take the square root of that. And then another constant, sine. So one cosine. It doesn't matter which one we write first. So like that. So that is the solution. So it's a sine cosine. We know the sine cosine are periodic functions. So that means if you look at the graph, it has a graph like this. So it's going to be periodic and it's going to fluctuate. It start with some value depending on the initial condition, and it's going to go in a sine curve or cosine curve because it's a mixture of that. So yeah, so that's what happened. So this is what we call a simple harmonic motion. This is everywhere, like all the atoms in the body follow these kind of motions. And if you have a mass and a spring, it's gonna follow these kind of patterns. So this is like kind of very common. So it's called the simple harmonic motion. And then the fourth one, what we normally call the hybrid model. So we have a hybrid model. What's a hybrid model is we have the exponential growth and the exponential decay. You can combine them into one. That's a hybrid model, and you can see the interesting relation. It is simply the same equation we just write above, but with the plus sign. So that's very interesting. What happened? There's no t here. It's the plus sign, the above one, but with the plus sign, we still put the k squared. So what's going to happen? We can write the solution of this one in two different ways. The one way is using the hyperbolic cosine and hyperbolic sine function. So cos kt plus sin kt. We put h to mean there's a hyperbolic functions. And then if you are not familiar with this, you can look at the video for that. We explain that, and we also talk about some other properties. For example, derivative. One of the major thing is that when you take the derivative, cos becomes sin and sin becomes cos. There are no negative signs. It's one of the major difference between the regular sign and cosine. Also, you can write this solution in different way. I'm going to still use AB, but those are not simple AB, some other constants. But I'm still going to say AB. So A e to the, we can write one of them, let's say KT. Now it's a KT, and then plus B e to the negative KT. That's why we call the hybrid model. This is the exponential growth model, and that's the exponential decay model. So you add the two and you get the hybrid model. So that's the hybrid model for when you have that difference equation, that's hybrid. So those are the four fundamental model equations. And if you look at the graph, so you're going to get like graphs like this. So I'm going to put both together. So you can get a graph like that. So because it's a part sine, part e to the kt, part e to the minus kt. So whoever the win gonna get the formula. So it's gonna be like that, or like it can be like that. Okay, because we know that if you hang a wire, heavy wire, it's gonna go in a equation like that. So it's like in many situations, and yeah. Good. Now let's try to see how to solve a problem using these models. So the goal is, if you see one of them, you can directly write the solution. Okay, because these are familiar one. Remember this. This is very useful for your other courses. So you can directly use the results. So let's look at a problem. So let's solve this problem. So we have, let's say, solve the initial value problem, d squared x over dt squared equal minus 4x, along with x0 equal, let's say, 12, x prime 0 equals 0. Why we need two conditions? Because this is a second order differential equation, so you need two conditions. Now what we can do, we're going to match this equation with one of those four models, and you can see that this is the simple harmonic motion situation. And you can see that in this problem, k squared equal 4. This implies k equal 2 because we consider only the positive value. Now we can write the general solution. So the general solution is, so the general solution is, you can say xt equals, you can directly write it. It is a cos 2t. The 2 is t is the independent variables. You have to be careful. So the independent variable goes there. Okay, and then also this x and this has to be x. Otherwise, it is not this type of problem. Good. And then so we have plus b sine 2t. So we have that. So that's it's directly come from the four model equations. Now what we can do, we can use the initial conditions, but we can see that when you want to write use the initial conditions, there's a prime. So that means let's take the derivative first. So taking derivative, so we can write x prime t equal, so what's the derivative of this one? It's a cosine. So derivative means the negative sign, but there's a 2 here. That means by the chain rule that 2 comes out. So that's going to be negative 2a sine 2t plus. Same thing, sine, when you take the derivative, it's going to be cosine. So it's going to be 2b cosine 2t by the chain rule. Now we can use the initial conditions. So using initial condition, we have x0, that means plug in 0 for the t. So you're going to get a cosine 0 plus b sine 0, which is equals to 12. This is given. Now we know that cosine 0 equals to 1, sine 0 equals to 0. So because of that, this simply implies that a times 1, that means a, plus 0 equal 12, that means a equal 12. So we find one value. Now using the other condition, we know that x prime 0, which is equals to the second one, so negative 2a, you can actually put the value here. So it is, we already know the value. So I'll put the value here just to make the calculation easier. So 12 sine 0 plus 2b cosine 0, which is equal to 0. So again, we know that the sine 0 equals 0, cosine 0 equals to 1. So that means this says that, so nothing comes from the first term. So this says that 2b equals 0. So this says that b equals 0. That means the b term is going to go away. That means therefore the solution is, therefore the solution to the initial value problem is simply xt equal 12 cosine 2t. So that's the solution of the problem. Good. So let's go to the next topic. So what's the next topic? So what we're going to do, we're going to talk about the classification of differential equations. So number 3, the classification of differential equations. Classification of differential equations. So we talk about various types. So we first start with what we mean by an ordinary differential equation. Ordinary differential equation. So we normally call this ODE. In this one, what we have, one independent variable, variable. So we have one independent variable. So an example would be something like this: dx over dt plus 3x equal t plus 1. You can see the independent variable is t, and thus there are no more independent variables. So these are ordinary differential equations, ODE. And then the next type is what we call the partial differential equation. So we have partial differential equations. Partial differential equations, partial differential equation, or we call this is a PDE. That's a shortened form for that. PDE, partial differential equations. So what we have, more than one independent variable. More than one independent variable. So there are more than one independent variable. Sometimes the space and time, those are the two common independent variables. So so such a differential equation have a kind of form like this. So we can write, let's say u is a function of x and y. So then we can write it like this. So if u is a function of x and y, if u is a function of x and y, so that u is a function of x and y. So that's how we write it. So then you can write a differential equation like this. We can say we can use the daba for that. So daba u over daba x plus 3 times daba u over daba t equal, we can say, x plus t. So this is a partial differential equation, and you can see that there are two independent variables, space and time. So x and t are independent variables, but that is a different course, and we are not going to focus that in this course. This is only for partial differential. This is only for ordinary differential equations, except in few cases, because we need the idea of partial differential equation in certain situations, and other than that we are not going to focus on that. Okay, that's about that. So there are two independent variables in this. So these are the independent variables. Independent. Okay, so there are two. In the first one you only have one. Okay, and then we talk about what we mean by a order of a differential equation. So that's the next topic we talk about, the order of a differential equation. So order means the highest derivative appear. Highest derivative is what we call the order. So for example, if you look at this differential equation, d squared y over dx squared plus x equal 3. So you can see the highest derivative up here is 2. So we call this is a second order differential equation. We don't say a 2 order. So we say this is a second order ODE. Second order ODE. Good. That's the highest derivative up here. The question, why you do that? Because you know that depending on the order, we had to use different techniques. So that's the major point here. So the next important topic is what we mean by linear and nonlinear equations. So the next one is number 4, linear and nonlinear. So linear versus nonlinear. So that means linear means no powers other than one of the dependent variable. So you're going to see no powers other than one. Other than one of the dependent variable. So we don't worry about the independent variable. So there can be only powers of one. So that means there are no products. Okay. So in other words, no products. No products of the dependent variable or its derivatives. So let's talk about two examples. If you say x is the dependent variable, So we can write dx over dt plus t cube x equal t. So you can see that there are no powers of x other than 1. So this is a linear equation. T3, t is the independent variable, that's okay. So this is linear. And if you look at this one, x times dx over dt plus the same thing here, t3x equal t, this is nonlinear. So those two equations make a big difference when you try to solve. Linear equations are easy to solve. Linear equations are easy to solve. So that's the fact. Linear equations are easy to solve. Good. So these are linear, nonlinear. Good. And then talk about what we mean by the constant coefficient. So number 5, constant coefficient. Constant coefficient. Constant coefficient equations. So that means all the constants are coefficient. All the constants, all the coefficients. Oh, I'm sorry. All the coefficients are constants. Okay, all the coefficients are constants. So for example, 5x double prime minus 3x prime plus x equals 0. So this is a constant coefficient differential equation. You can see that all the coefficients are just numbers. What we normally do is we consider a characteristic equation to solve. Okay, so use characteristic equation. Use characteristic equation to solve. Which remember which is in lambda. So we write a lambda equation. Good. And there's a characteristic equation for matrices as well. But here we call the characteristic equation for that because that can characterize the differential equation. Okay, that's a constant coefficient. And then let's talk about homogeneous versus non-homogeneous. So the next one, so we have homogeneous versus non-homogeneous. So be careful, the homogeneous and non-homogeneous has a two different meaning in differential equations. And then we can talk about the homogeneous and non-homogeneous again later. So here, what we mean by the homogeneous is whether the differential equation equal to 0 or not. So like it will be easier from an example. So for example, if you have 5x double prime minus 3x prime plus x equals 0, you see that. So you can see that. So you're gonna set the differential equation to 0. That means that side is not a function of the independent variable. So all the dependent variable you can put it to one side, and then you can see that. So we can write this one as a this is what we call a homogeneous equation. So homogeneous equation. So no functions of the independent variable. Okay, so it's a homogeneous equation. Now you can say 5x double prime minus 3x prime plus x equal t. This is non-homogeneous because it's a function of the independent variable. Okay, so if you have a function because you can always pull all the dependent variable terms to one side, and then if you see a function of the independent variable alone, that's going to be non-homogeneous. Okay, you see a function of the independent variable alone. A 0 we just say other than 0. Okay, because 0 is also a function, but other than 0. So this is what we call non-homogeneous because of that t term. So this is non-homogeneous. Good. homogeneous and non. So there's a function of the independent variable alone. Okay, so that means let's write that. So there is a function of the independent variable only. Independent variable only. Okay, so if you see a function of independent variable only, it is what we call non-homogeneous. Good. And then we have what we call autonomous differential equations. So what's autonomous means if the differential equation does not depend on the independent variable, we call it as an autonomous differential equation. So differential equation does not depend on the independent variable. Okay, if the differential does not depend on the independent variable, we call it as a autonomous differential equations. Let's write this one. So you can say dx over dt plus x squared equal 3. So you can see that this does not depend on the t variable, so this is autonomous one. Okay, so this is autonomous. So if you had like a function of t somewhere, so it is non-autonomous. It's autonomous one. Okay, and then the last topic of this is what we call system of ODEs. System of ODEs. So a system of ODE, so not just one equation, but there are many equations. So like for example, x prime equal 2y plus e to the t, y prime equal, let's say, 3x plus y sine t. So this is what we call a system of ODE. So we discuss all of these types. Good. So that's about that. So I don't discuss any further examples of this one, but if you need more examples, you can look at the corresponding lecture for that. But this is the kind of basic ideas we talk about. Let's go to the next topic. So the next one is what we call the basic integration. So number 4, basic integration. Basic integration. So this is the very simple thing that we did. We did even this one in Calc 1. So there are two types. So let's go with the type 1. So what's the type 1? You have a differential equation which is just on the right side, it is just a function of the independent variable. So this is a function of the independent variable. So this is a function of the independent variable only. Independent variable. So if this is a function of independent variable, things are very easy. Just integrate the two sides. So that means y is simply the derivative of y is simply the integral of the derivative. Okay, we're just going to integrate with respect to x so that they cancel each other. So that means simply become the integral of fx dx. So it's very simple, just integrate. That's going to happen if the derivative is a function of the independent variable only. So this is the easiest case. You can simply integrate that. You gotta be careful because sometimes it's not the case. Okay, so let's talk about type 2. So what the type 2 is, so type 2, we have dy over dx, but it is a function of the dependent variable now. Okay, so if you get the function of the dependent variable, so let's write. So what happened now is a function of the dependent variable. So what we can do in this case, we can flip the equation over. So we can write this one as dx over dy 1 over gy. Now you can see that this came back to the previous case, because you can simply consider y as the dependent variable in this case. So we can see consider y as the independent variable. So that's the whole point. And then just integrate the two sides again with respect to y now. So that means you're going to get x, which is the integral of dx over dy with respect to y, not x, integral of gy dy. So that's what's going to happen in that case. You're going to integrate with respect to y. Okay, those are the first type, what we call the basic integration. So you can just use a table of integrals for that, the common ones, and you can do a lot of problems just using these two equations. So the first case is the derivative is a function of the independent variable. Second one is a derivative of the function of the dependent variable. In the second case, we're going to flip the equation over and integrate. So let's do two examples from those two types. So we have this first example. So let's say solve the initial value problem. Let's say dy over dx equal 3 cosine x, 3 cosine, let's say 2x, minus 8 e to the negative 4x plus 5 along with y0 equal negative 3, something like that. And what do you notice? You notice that this is the independent variable. This is the independent variable, and you can see that it's only a function of the independent variable. So that means this is the case 1. That means you can simply integrate the two sides. Okay, so you can see the function of, so this is a function of x. Okay, x is the independent variable. So that means we can integrate. So by integrating, just integrate. Okay, by integrating, y equal just the integral. So it is 3 cosine 2x minus 8 e to the negative 4x plus 5 dx. So this is just very basic integrals, and if you forget, so these are the kind of formula that we're going to use here. So if we have e to the kx dx, the answer is simply 1 over k e to the kx plus c. This only works when k is a constant. And the second one, if we have a cosine kx dx, and we know that it is simply 1 over k sine kx. So just divide by k. And the other one, if we have a sine kx, k has to be a constant. So this is simply negative 1 over k cosine kx plus c. So those are the kind of three common ones. And then also we have the power rule that everyone know. And so this is what we're going to use now. So that means in this case k equal 2. So simply divide by 2 is a cosine. That means it's a sine one. So divide by 2. So that means it's going to be 3 halves sine 2x minus, you can see 8. You have to divide by negative 4 e to the negative kx plus 5 is a constant. So it's a 5x plus c. So that's what you get. And you can simplify this a little bit. So you're going to get 3 halves sine 2x. Simplify, you get 2 e to the negative, this k actually 2. K actually 4. So you get 4. So e to the 4x plus 5x plus c. Now what we can do is we can use the initial condition. So using the initial condition, y0 equal -3. You can see that -3 equal y0. That means wherever you see the independent variable, plug in 0. So you're going to get 3 halves sine 0, which is 0, plus 2e to the 0, which is 1, plus 0 plus c. So you can see that this is 0 and this is 1. So this tells you that -3 equal 2 plus c. So in other words, c equal -5. So you can plug in that. So that means the solution is simply y equal 3 halves sine 2x plus 2 e to the 4x plus 5x minus 5. So that's the solution. So you can see that it's not difficult. We just use the basic integration technique because the right side is just a function of the independent variable. Now let's look at the other type. So what's the other one? This example. So we have, let's say, solve the IVP, the initial value problem, dy over dx equal y plus 3 along with y1 equal -2, something like that. So if you see an equation like that, now what we can do, you can see this is a function of the dependent variable. So this is a function of the dependent variable. So when you see function of dependent variable, what you do, you're going to flip this over. Also, you can do this problem using the separation of variable. Actually, that's a separation of variable, but you can see as a technique, you can remember like that. So we're going to flip this over. So we can write this on dx over dy equal 1 over y plus 3. Now what we can do? Integrate with respect to y. So integrate with respect to y now. So if you do that, you get x here, and it's simply the integral of 1 over y plus 3 dy. So you can see that's the 1 over y plus 3. 3 is just a constant, so this is a log function. So this simply becomes natural log y plus 3. We are not going to use the substitution here. That's like long time ago. Okay. So we have the solution now. So what we're going to do is we can find the constant, and then so I mean there are two ways to do it. First we can solve for y and then plug in the constant, or we can find the constant and then we can solve. So let's do that. So we know the constant. So what it says that, so using the initial condition. Okay, so there are two ways to do it. Either you can use the condition now and then go for the solve for y, or solve for y and then find the constant. So it work both ways, but be careful what you get. Okay, because sometimes when you try to write the log form with the exponential form, remember you get plus or minus, so you have to be careful with that, whether that is the case. So let's solve for y first. So what we're going to do now is you can write this one as ln y plus 3 equal x minus c. So this says that y plus 3, we have solved many problems like that. So you can see that this is absolute sign. So that means you're going to get the plus or minus here. So we have it's a plus or minus. You can see e to the x minus c. So now what we can do, we can write this one as e to the like plus or minus e to the minus c, and then e to the x. What I'm going to do, I'm going to call this whole thing just a C. So if you do that, or some other letter if you want, just what we normally call the by abyssal notation, I'm going to call this whole thing just C. It's not the same C, but another one. Okay, like that. So we can write it like that. So in other words, y equal CEX minus 3. Now we're going to use the initial condition. So using the initial condition, we know that for the initial condition, it's a negative 2 when you plug in x equal 1. So let's do that. So that means negative 2, y equal negative 2 equals CE negative 1, negative 3. And then we can, what we need to do is we need to solve for C. So let's do that. To do that, first we're going to move the number to the other side. That means we're going to add 3 to the both sides. So this says that 1 equal CE negative 1. In other words, if you multiply both sides by E, it says that C equal E. So if you plug in C equal E, what's going to happen? Y equal E times e to the x minus 3. Okay. So and then you can combine them because e means e to the 1. So if you combine that, so you're going to get y equal e x plus 1 minus 3. So that is the solution. Yeah, I see that there's a small typo here because we plug in negative 1. It's not negative, it's positive. So that means there's no negative sign. So that means this is going to be e to the negative 1. So that means this is negative 1. So that means the final answer, this is minus 1. Good. So that is the solution of the differential equation. And you can see that that's not that difficult, but there's a process that we need to remember. Good. So let's move on. So let's talk about the next major type. So what is the what we call the separable differential equations? So number 5, a separable differential equation. Separable differential equations. So what's the separable differential equation? So let's look at the differential equation. We have dy over dx, which is a function of x and y. But sometimes what happens, you will be able to separate them into, you will be able to write this fxy function as a product of function of x and y. So if you can write this one as a product of fx and y, we call it is a separable equation. So this is what we call a separable differential equation. If you can do that, we call it a separable differential equation. Separable differential equation, because you can separate them. Okay. And after we do that, what we can do, we can divide both sides by gy. So if you divide, you can write this one as dy over gy equal, on this side we have fx, we're going to multiply, we're going to bring dx to the other side. So we can separate y's and x terms, and then after that what we can do, we're going to separate, we integrate them separately. So that is what we call the separable equation formula. Okay, so we're going to integrate them separately. Okay, very simple argument. We're going to first write as a product, and then we're going to move the gy to the other side by dividing, and then integrate the two sides separately. So let's look at some examples. So let's say solve dy over dx, doesn't look like x, dy over dx equal, let's say y minus 4xy, and then y0 equal, let's say e something. So when you get a problem like that, you're going to check whether you can write this as a product of x and y separately. So that's the first step. So the answer, and you can see that yes, you can write the right hand side. If you pull y out, you can see 1 minus 4x. You can see it's a product of x and y separately. So what we're going to do, we can divide this side by the y function leave the x function on this side and then integrate with respect to x on that side, integrate with y on this side. So that's the major step. Now what we can do, we can integrate the two sides separately. First one with x, left side with y, right side with x. So you're going to get ln absolute y here. This is just the power rule. So you're going to get x minus, if you integrate x, you get x squared over 2. So that means you can 2x squared plus c. We are not going to add c1, c2. We only add one c to one side because you can always simplify. Now we can write this one using the exponential form. So let's do that. So if you write them using the exponential form, I can do it here, then you can see all the work. So if you write the exponential form, so what's going to happen is y equal the same thing. We know that's absolute value, so you get plus or minus, and then you can just put one constant. So it's the same thing here. So it is so what happened is plus or minus, and then e to the x minus 2x squared plus c, and then what we can do, the plus or minus and then e to the c, we're going to combine. So if you combine that, let's write that extra step. So if you combine that plus or minus e and the c, we're going to combine. So that means I'm going to call it a. So if you call that a, and then you're going to get ex minus 2x squared. We have done this a lot, okay? So that's plus or minus e to the c, you could just call a, and we still have e to the x minus 2x squared. Good. So that's the solution. Now what we can do, we can use the initial condition. So the using the initial condition that y0 equal e, so we're going to get e equal a, e to the 0, e to the 0 means 1, so that means a, so a equal e, so that means y equal e to the 1, we have e x minus 2x squared. This means that's e to the x minus 2x squared plus 1. So that is the complete solution. It's not difficult. Okay, first we find the general solution. That's the general solution, and then we use the initial condition to find the constant. Good. Let's just do one more example. This is very important topic. So how about this example? So the next example, let's say solve x dx over dt equal 3e to the t minus x, something like that. So let's try to find the general solution of this one. So what is the independent variable? Independent variable is t. You can always switch, flip it, and then change that. So it doesn't matter. At the end, you're going to get the solution again. Okay, so the answer. So what we're going to do, we're going to use certain algebra here. So we write dx over dt. We can write this one as 3 e to the t times e to the negative x. So we can do that. Now what we can do, we can see whether we can move x terms to one side, t terms to the other side. Actually, you can see that yes, we can do it. If you multiply both sides by e to the x, you're gonna get x e to the x dx, and then I'm gonna leave 3 here. I leave et here, and then dt I'm gonna move to the other side. So that we can do. So you can see it is a separable equation now. So we can integrate the two sides separately. Right side is okay. How do the left side? For the left side, you have to use the integration by parts. Okay, so we're gonna make the table. So we're gonna pick u equal x. You can use the shortcut. You can use the di method. I'm going to just use this regular method. Okay, just to make sure that. Okay, so dx dv. So if you are trying to use the shortcut method, the di method, make sure that you practice that first, okay? So DI method, and there's a video and that kind of solve many problems there, so you can practice using that. Okay, and then we take the derivative here, so the du equal dx, integrate, so you get ex, and then what is the integration by parts formula? It is udv is simply equals to uv minus vdu, so that is the integration by parts formula, so we can use that. So by the integration by parts formula, on this side you simply get uv, that means x ex minus vdu. V means ex, du means dx, equal, here 3e to the t plus c, we add only c one side, and then we can finish the integral here, so we get x ex minus ex equal 3et plus c. So the question is, can you solve this for x? X is the dependent variable. Can you? Because of that x term, we cannot. Because there's no way you can pull the x term out. Because when you have sine, cosine, exponential, log, like that, there's no way you can pull the x term out when you have a product like that. It's a nonlinear. Okay, so this makes it nonlinear. So we cannot. So we can leave it like that. So this is the implicit solution. So this is the implicit solution. So implicit solution of x. And if you have initial conditions, what you can do is you can plug in them and then solve for c. But otherwise, you just have to leave it like that because there's no way you can solve this. But that's the implicit solution for the x function. Very good. Okay, so let's talk about the next important type. That is the first order linear differential equations, and we're gonna use the integrating factors method. That's the next major topic. Okay, you always have questions in the exams. Good. So let's talk about that now. So the next topic, this is number 6. So this is first order linear differential equations. You have to remember like that, first order linear, so we use the integrating factor method. Integrating factor method. So let's talk about the let's recall what we did. So we write what we call the standard form. So it has to be of this form. If it is not, you have to bring it to this form before we do anything. And then dy over dx plus pxy equal qx. So that's the kind of format for the first order linear. This is what we call the standard form. Standard form. And then, so if it is not in the standard form, you have to bring it to the standard form first. Okay. So if not, bring it to standard form. That's the first step. Bring it into the standard form. And if you don't do that, your answer is wrong. Okay, so it's very careful with that. You have to bring it to the standard form. Good. So let's talk about the steps. So what are the steps of such a problem? So the first step is, so we assume that it's in the standard form. Okay, that's the standard form. So we assume this is the case. Now what we're gonna do, we're gonna find what we call the integrating factor. Okay, so find the integrating factor I, which is always e to the px dx. P means everything. You're gonna with the sign. So we're gonna calculate that. After that, what we can do, we're gonna multiply. We're gonna multiply the whole equation by that. So we can write I x times the dy dx plus px ix times y on the other side we have qx times I. Now the magic happened. What's the magic? You can see that on the left side, this is automatically the product rule for the product y and I. So we can write the form. That's what we normally call the form. So what the form here is automatically this side becomes the product of y and I. That's automatic. That's the product rule. If you apply the product rule, that's what you get. And on the other side, now we have qx and I. Now what we're going to do, to remove the derivative, we can integrate both sides. So you can integrate. And once we integrate, what's going to happen? You get yi term on this side. This is just the integral qx ix. So you can see this is a function of x. It may or may not be able to integrate. If you cannot, we leave the with the integral sign dx, and we can exaggerate the plus sign. Now what we can do, we need to solve for y, so you divide by I. So that means y is simply, you're going to divide by I term. So you're going to get the bracket. So we have, inside that we have qx ix dx plus c. So those are the steps. So let's try to, don't remember this as a formula. That's because it's much easier to follow the steps and get this quickly. That's exactly the whole point of learning these things. Okay, plugging to equations, anybody can do that. So it'd be better to like kind of follow the steps and get that. Good. So let's do maybe 2 examples from the topic. This is very important. So I'm going to do 2 examples. This is the first example. So example number 1. So let's say we have dy over dx minus 3y equal e to the 3x sine 4x y 0 equal negative 1/4. So the answer, so you can see that this is a first order linear differential equation in the right form. Okay, so this is first order linear equation. So that means we're gonna use the, you can see that this is not separable equation. You cannot separate x and y. So we can use the integrating factor method. So let's go step by step. So we're gonna find the integrating factor. So we're gonna say I, which is e to the px dx. So let's plug in here e to the, what is the px? You can see px is with the sign negative 3. That's the p. So it is negative 3 dx. Negative 3 you can pull out. So that means it's going to be e to the negative 3x. We are not going to add the c. Because we are looking for one solution, not all the solutions. Now what we can do, we can multiply. So you can multiply the whole equation by that. So it is e to the negative 3x dy over dx minus, we have 3 e to the negative 3x y equal, what we get on the other side? It is e to the negative 3x e to the 3x sine 4x. You can see it simplifies very well. Okay, so that means if you simplify it properly, it's going to work very well. So you're going to get sine 4x. Okay, that's the gift you get if you did that right. It simplifies very well. Good. Now we know that this is automatically, this side is, so we can write the form. So this is automatically the derivative of the y and the integrating factor. So that is automatic thing. On the other side we have sine 4x. To remove the derivative, we can integrate. So integrate with respect to x is the independent variable, so that's going to cancel out. So you simply get y e to the negative 3x, the integral of sine 4x dx. This is very easy to integrate. K equal 4, so you can divide by that. This is sine, so it's a negative cosine. So this can be negative 1/4 cosine 4x plus c. Don't forget that. Now what we can do, we can multiply both sides by e to the 3x. So if you multiply by e to the 3x both sides, so you're going to get negative 1/4 e to the 3x. When you multiply by e to the 3x, is opposite sign. Okay. So negative 3, you multiply by positive 3. So that they're going to cancel on the left side. On the other side, you multiply by e to the 3x. So you're going to get that times cosine 4x plus c e to the 3x. So that is the solution. That's the general solution. Okay, so this is the general solution. Now what we're going to do, since we know the initial condition, let's plug in that and try to find c. Otherwise, this is the solution. So if I need to find general solution, we're done. Okay, so next step is we're going to use the initial condition to solve it. So using the initial condition, y0 equal negative 1/4, you're going to get negative 1/4, which is simply equals to y0. This is negative 1/4. Wherever you see x, put 0. So e to the 0 cosine 0 plus c e to the 0, which simplifies to negative 1/4, because we know that the cosine is 1, e is 1. This is also 1. So you're going to get negative 1/4 plus c. You can see negative plus 1/4, negative 1/4 get cancelled. So this says that c equals 0. So that means that term is gone. So you simply end up with y equal negative 1/4 e to the 3x cosine 4x as the solution to the initial value problem. Good. So let's try to solve one more of that, because this is very important. So I'm going to do one more. So then as the next example, let's try this. So the example, solve, let's say t dy over dt minus 2y t cube e to the negative 2t. Okay. Good. Is this in the standard form? So that's the first question you want to ask. Okay, first question you want to ask whether this is separable, because that's much easier. Actually, that's not the first question. First question is whether this is the basic integration problem. Is this like dy over dt equal a function of the independent variable only, or function of the dependent variable only? And you can see that no, it's none of them. So it's not basic. And then ask whether this is a separable differential equation. Can you separate the x term? Can you separate the y terms and t terms? And you can see that there's a sum, and also there's a multiplication. There's no common term, so this is not separable. And then we're going to go for the linear first order, the integrating factor method. So when you go to integrating factor method, you ask the question, is this in the standard form? And you can see that this is not in the standard form. So what are you going to do? You have to bring it to standard form. So how to do that? You're going to divide by t. So because you don't need that term. So that's the only problem. So we're going to divide by that first. So let's do it. So we're going to divide the whole equation by t. So that's the first step to do. Okay, so we can write not in standard form, not in standard form, not in standard form. So divide by that t term. Once you do that, so you're gonna get dy going to get dy over dt minus 2 over ty equal, this becomes t squared e to the negative 2t. Okay, now this is standard form. Everything looks good. Now what do you want to do? Find the integrating factor. So let's do that. So the first thing we did was divide. Okay, so find the integrating factor. So which is I equal e to the integral of pt, now pt dt. So it is e to the integral of pt, which is negative 2 over t. You have to pick the whole thing. Okay, dt. This is very easy to integrate. We normally do pull the negative t out. This is 1 over t dt. 1 over t means ln. That means e to the negative 2 ln t. We're going to bring this as a power. So that means we can write this one as e to the ln t negative 2. Now from algebra, this part get cancelled. Okay, so you're going to get t e to the negative 2, or in other words 1 over t squared. It doesn't matter which form you write. So that is the integrating factor. Now what we're going to do, we're going to multiply the equation, our standard form equation, using by the integrating factor. So let's do that. So when you do that, so we're gonna multiply by 1 over t squared, the whole equation. So you're gonna get 1 over t squared dy over dt minus, it's gonna be t cubed now, y equal, what happened here? It is 1 over t squared. What you have here? You have t cubed e to the negative 2t. So you can see this get cancels very well. And then you have e to the negative 2t. So then we can write the form. So that this side is automatically become the, so we write the form. So this side automatically become d over dt y times the integrating factor. Other side is e to the negative 2t. We can integrate this now. So if we integrate, you get y times 1 over t squared. This is the integral of e to the negative 2t dt. This is a very simple integral. You're going to divide by the constant. So that means it is negative 1/2 e to the negative 2t plus c. Now what we're going to do, we're going to multiply both sides by t squared. Okay, so multiply by t squared to cancel that. So we're going to get y equal, you're simply going to multiply by t squared, so you're going to get negative 1/2 t squared e to the negative 2t plus c t